Hello. We are working our way towards a big theorem, Theorem 8 in section 2.3, and we need a couple of tools to get there, a couple of facts, some of which I can prove here for you, and two of which I'm just going to be doing examples. But they are facts you need to be able to utilize and answer questions about. So let's get going. All right. So the first one is that any elementary matrix is invertible. So lemma 1, this is not really a proof. This is more just like demonstrating what's going on in some parts. In other parts, it's fairly straightforward, right? So let's let E1 be an elementary matrix that performs the elementary row operation of switching rows, right? So let this be the one that performs the operation that switches rows I and J, right? Okay, so that's the first type of elementary row operation we were considering before, so I'm going to make that the first type of elementary matrix. Remember how we construct E1. Start with an n by n identity matrix and perform that elementary row operation on it. Switch rows I and J. Right, what is that going to look like? Let's see. So if this is my n by n matrix, identity matrix, it's got a bunch of ones on the diagonal, zeros elsewhere, right? And so if this is an n by n identity matrix and I perform that row operation on it, where I simply switch rows I and row J, let's say this is, let's just assume that I is less than J, so let's say this is the ith row here. Well, normally in an identity matrix, the one would be at the ith place, right? But we are going to switch that row, which looks like this, a bunch of zeros elsewhere. Right, we're going to switch that down into the jth row place. Okay, so I'm going to put that right there, and a bunch of zeros elsewhere. Right? So it's now sitting in the jth row. What was in the jth row? In the jth row was something that had zeros up until we got to the diagonal to the jth place. So that's now up here. So this looks like a bunch of zeros. In particular, right at the ith place, there's a big fat 0 instead of the usual set of 1s. So right above this one, right, is a 1 on the diagonal. Then there's this 0. Then there's more 1s. Keeps on going until we get here. Instead of having a 1 in the jth place, now we have a 0, a bunch of 1s. Keep on going. So everywhere else it's a 0. Okay, so how does a matrix perform this row operation on a matrix A? So E1 multiplied by A switches rows I and J. Right, we talked about that in the last video. So if I do that to the identity matrix, right? Well, I'm just going to get E1, right? Because anything multiplied by the identity is itself. All right, now if I multiply it by another one of the same matrix, so if I have E1 multiplied by E1, E1 was this matrix here with the things switched. If if I multiply it again on the left by E1, what's that going to do? It'll switch rows, i's, and j. So that'll get us back to the identity. Well, that statement right there says that there exists a matrix such that E1 times that matrix gives me the identity, and there exists a matrix such that that other matrix multiplied by E1 gives you the identity. So that implies that E1, its inverse, is itself. Okay, so that's the first part, part one. Switching, the elementary matrix that switches rows has an inverse, any such. Part two. Okay, we have to show that if we let E2 perform the second row operation, what does that look like? The second row operation was a new row I is equal to the old row I multiplied by alpha, where alpha does not equal to 0, right? Okay, so again, to construct E2, we just take an identity matrix and perform that row operation on it. So E2 looks just like an identity matrix. We have a bunch of ones. And then all of a sudden, on that ith place, we're going to see an alpha appear because we multiplied the ith row by alpha non-zero. So zeros everywhere else, right? Alpha times all those zeros, just going to be 0. Same thing here, just a bunch of zeros, except at that one spot. Everywhere else, it looks like the identity matrix, right? So that's what E2 looks like for some alpha not equal to 0. All right. In fact, what I'm going to do for this one in particular that multiplied the ith row by some alpha, I'm going to call this E2 1 alpha. All right. Let's let E2 I 1 over alpha, since alpha is not equal to 0, remember that implies 1 over alpha exists as a real number. So let E2 I 1 over alpha look like this. Same sort of look, pretty much everything the same except in that ith spot, we're going to have a 1 over alpha. So ones, 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 zeros elsewhere. Okay, how do we get that? By performing the operation new row I is equal to the old row I multiplied by 1 over alpha. Okay, multiplying any other square matrix of the same n by n dimension by this matrix will multiply its ith row by 1 over alpha, right? So that means that if we had E2 I 1 over alpha multiplied by E2 I alpha, well, multiplying this matrix on the left by that one is going to give us essentially something that looks just like the identity until we get to that ith spot. What's it going to look like? It's going to have 1 over alpha multiplied by an alpha. Everything else looks just like the identity matrix. But of course, 1 over alpha times alpha, that is 1. So this is the identity matrix. Same thing is true if we took this multiplication in the different order. If we took E2 I alpha and multiplied it by E2 I 1 over alpha, this matrix would start out looking like this. You multiply it on the left by that one, it's going to multiply this one by an alpha in that ith row, because 1 over alpha, so this is equal to this. Since 1 over alpha times alpha is the same thing as alpha times 1 over alpha in R, right? So we have these two types of elementary matrices are invertible. Third part. Part 3. Let's let E3 be the elementary matrix that performs the third type of elementary row operation. Okay, what does that look like? Well, you just perform that third elementary matrix representing the third type of elementary row operation that looks like new row I is equal to old row I plus alpha times row J, where alpha is not equal to 0 and I is not equal to J, right? What does that one look like? That looks like this. E3, again, it's going to look mostly like an identity matrix, okay? But let's focus on those two rows I and J. So if it was just the identity, we'd have ones, come down to the ith row, we'd still have a 1 there. If it was just the identity matrix, a bunch of 1s, get down to the jth row, let's say that's right about here, here's the ith row. Again, we would just have 1s, and 1s all the way down along the diagonal, and 0s elsewhere. That's not yet E3, okay? But to make it E3, we're going to switch, well, not switching rows I and J. We're going to make a new row I by adding to it alpha times row J. So if this is the JJ entry right here, I multiply that by alpha, well, and then add it to row I, I'm going to have this up here in row I. I'm going to have alpha times that 1 up here, and a bunch of 0s elsewhere. Notice there was a 0 over here in that jth row. I think that jth row is not changed. It's just a bunch of 0s all the way across, except for that one on the diagonal, right? So if you multiply that by alpha, you only pick up something non-zero here. That 0 that's here added to that 1 is still just 1. So that's the only new entry, apart from, yeah, that's the only change from an identity matrix, right? Okay. Well, that's E3. E3 inverse, a matrix that will undo that. If I call this one, sorry, not just E3, excuse me, but let's say E3I alpha J to suggest new row I by adding alpha times row J, right? So E3I alpha J inverse is going to be E3 type matrix with I minus alpha J. So if you will allow me, I'm just going to say that that matrix looks like that one above, but now instead we would have a minus alpha times 1 here. Okay. So if you now multiplied these two matrices, one by the other, in the one case you're going to be adding alpha times row J to row I, and in the other case, in this one, you're going to be subtracting it. So if you start with this one and then multiply by that one, the plus alpha j, alpha times 1 in the jth spot, added to the opposite of alpha, well, that's just going to be equal to 0. So that's going to turn that ijth entry, this is the ijth entry, that's going to turn that ijth entry into a 0 again. Doesn't matter which order in which you do it, because that is equal to this. And they're both equal to 0. So, therefore we have that the inverse of I alpha E, I alpha J is I negative alpha J. Okay, so I'm gonna have to come back in a second video and do the other 3 lemmas. So that'll be part 2.